Hello everyone, I am Elham Shaabani from Arizona State University. My presentation is on early identification of violent criminal gang members. Gang violence is one of the major problems in the United States, accounting for 20 to 50% of homicide in the major cities. Law enforcement has an existing data on these groups, for example, the underlying social networks, and which has been shown by Papachristos to be useful for enabling smart policing tactics. What we are looking here is to identify potential violent offenders to help police to use its resources more smartly. We don't want to direct arrests. What we are looking for is to direct police presence in time and violent spike. What we have is a co-arrestee social network as well as some metadata on each of these arrest incidents. We didn't leverage features that use race, gender, and ethnicity of our individuals. We leverage a combination of social network analysis as well as supervised learning methods. We designed two different experiment setups. The first is we consider that we know the entire social network. We get the precision of 0.89 and the recall of 0.78. In our second experiment setup, we consider that the network is learned over time, and we get 4 times more true positive. Now I want to overview our network data. Our data consists of gang-related arrest incidents gathered from August 2011 to August 2014 in Chicago. As you see, our data is highly imbalanced with much more non-violent offenses than violent offenses. We create a social network of our data. The nodes in our network are the individuals who are arrested, and the links between them means that they are arrested together. We also studied the degree distribution of our network, which was exponential in comparison with a scale-free network, which has power law distribution. We also compare our network with a random network and a small world network. Our network has higher clustering coefficient and higher average shortest path in comparison with these two networks, respectively. Other characteristics of our data is that there are many instances of repeated offenses of the same offenders, which allow us to use this data for predicting future violent offenders. Another characteristics of our problem is seasonality of crime. As police observation, there are less violent and non-violent offenses in the winter months. Now I'm going to present the identifying methods, the methods for identifying violent offenders. There are two existing methods. The first is past violent activities. In this method, if an individual has committed a violent crime in the past, we claim that he will commit a violent crime in future. An obvious version of this method can be we return the set of individuals who has committed a violent crime in the in the past delta t days. The second method is two-hop heuristic, which is based on the result of Papachristos, which investigated the social network of gunshot victims in Boston. They found that there is an inverse relationship between the probability of being victim and the distance between and the shortest distance to the previous victim. However, the Chicago police has adopted this method and they use this to predict the offenders. And they also use the arrest and victim data, and we also use victim data, but it doesn't offer any significant improvement to our results. We evaluated different supervised learning methods, and the random forest was the best one. We classify our features into four groups of neighborhood-based features. These features are based on a given node and its immediate neighbors. Network-based features that they require more than just immediate neighbors. Temporal and geographic features, which are focused by literatures in criminology. Neighborhood-based features. These features are based on a given node and the first and or second level neighbors. One of the simplest features in this group can be the degree, which means the number of individuals who are arrested with a given node. We can extend these features to any sets of crimes of interest. For example, the violent degree, which means the number of its neighbors that has committed crime in our violent set. We also found that the combination of binary features can be useful, and we explore our space using these features. One of these binary can be if at least half of its neighbors in the network distance of I has committed any crime in the set C, we say this feature is true, and it's false otherwise. Network-based features. We categorize our features into two groups of community-based and path-based. Community-based features are based on our definition of community, either with algorithm or gang. Some of these features are triangles, the size of the group, the size of the connected component after we remove the given node. Path-based features are based on a set of nodes that has committed a certain crime. We adopted some of the measures in the literature, such as betweenness, closeness. We also studied the diffusion process based on tipping model in these features, and they proved to be effective. Geographic features. These features are based on the beat and the district of the location that an arrest incident happened. The intuition behind these features is, for example, if an individual has committed crime in a violent district, it's more probable to commit a violent crime in future. And our result is in accordance with the known literature in criminology. The last feature group is temporal features, such as average time duration of consecutive arrests of offenders, and the number of violent groups as time goes. We designed two different experiments. The first is we consider that we know the co-arrestee network. Using this network, we evaluate each of our feature groups: neighborhood-based, network-based, geographic, and temporal. Network-based features is highly correlated with violent behavior, with average F1 value of 0.72 compared to 0.63 for network-based, 0.21 for geographic, and 0.03 for temporal features. We also picked one feature from each of our feature groups. The intuition behind this experiment is that each of these features can be a representative of its group. And as you see, the network-based one is the best. In this slide, we compare our method, random forest, with THH, which is the baseline. I want to mention that, as I said, THH is an adopted version of what is proposed by Papachristos, and we are using it for predicting future offenders. And the last experiment for this, and the last figure in this experiment is the ROC curve of our features. The area under the curve for using all features is 0.98, and for each of which is the best, and for the other feature groups is 0.92, 0.98, 0.7 and 0.65 for network-based, neighborhood-based, temporal, and geographic features, respectively. The second experiment setup is we consider that the co-arrestee network is learned over time. This experiment is more difficult than the previous experiment that we did. In this experiment, we split our data into two parts. The first part for learning and identification, and the second part for measuring the performance. As you see, in the early months, we are missing about half of our graphical data, the nodes and the edges. And as time goes, our graph is becoming complete. But the problem is the number of violence offenders is becoming lower and lower, which increases the problem of data imbalance. In this slide, we compared the performance of our algorithm, FRF and RF, with THH and PVA. FRF is filtered random forest. We have removed all the individuals who has not committed any crime in the past 200 days. As you see, we got the best precision, but the PVA has better recall, and it's because of its high number of false positives, which make this method useless for the law enforcement because of its, as I said, its high number of false positives. In this slide, we compared the number of false positive and true positive. We removed PVA because of it produced between 1,500 to 3,500 false positive for each month. And FRF and RF are the best for with a higher number of true positive. And now we are working with Chicago Police Department to deploy our work in the operational environment, and the provisional patent has also accepted for this work. What we found is there is a strong relationship between the network-based features and violent crimes. We did two different experiments. The first was we considered that we know the entire network, which we get F1 score of 0.83. This experiment is unrealistically optimistic. That's why we designed another experiment that we consider the network is learned over time. We get 4 times more true positive. This experiment is also unrealistic going the other way. Since the police has some additional information from the internet, the social media, the informant reporting, intelligence reporting. However, we didn't have these data. Thank you.
Great, thank you. So we have plenty of time for questions about art. So I think gentleman in the black shirt first, and then blue, and then yes. Here.
Hi. So you mentioned in the beginning that you remove the obvious tags of race, ethnicity, and gender from the data before you start doing the analysis. But one concern that's often the case with this kind of data is that even though those features are not explicitly present, they could be implicitly present and correlated with features that are actually getting used. And I was wondering if you were did you try looking into see, are there in fact potential correlations or strong correlations between the features you removed and the ones that you're actually using for prediction, to the extent where maybe in some sense you are using those features to predict even if you're not directly using them? Do you know if there's any strong relationship of that kind?
We tried not to use these features, and we didn't consider these features. So maybe there are some relationship, but because of we don't want to be racist, that's why we didn't use these.
Okay, all right.
You're
right. Next to it, yes.
Thank you. I was just wondering, you identify gang members from the social network, right? But
we had gang affiliations of the individuals.
Okay, but do you give like a probability of them being, because there was like violent crimes and non-violent crimes, right, from the network?
Yep.
So do you give them a probability of how violent they will be, or to like prioritize for analysts to examine these criminals?
We say an individual is violent if he has committed a violent crime in his life in the past. So if he has committed any violent crime, we say he's violent.
But how do you assess, like, how do you prioritize that? You know, like some people might be more violent than others, given their networks as well in the future, I guess.
What is important for us is to find the violence in individuals, and we believe that if one person has committed violent crime, he's able to commit violent crime again. So there is no difference between these, because we can say maybe he won't commit a violent crime.
Okay, yeah, in the front.
Hi. Have you tried to sort of distinguish between features which are, I guess, causal versus predictive, in some sense? You know, to say, you know, this causes, for example, just to give an example, there's a recent book by Ta-Nehisi Coates called Between the World and Me, and he says that in inner Baltimore, for example, if you drop out of high school, then it's 60% chance that you'll, you know, end up doing some violent crime. Have you sort of tried to?
For example, in this experiment, we are just considering one feature group, so it's somehow near to what you are asking. When we consider just the network base, just neighborhood base, we are evaluating these features' performance, and the network base is the best group of features.
So somebody wanted to intervene and say, okay, we want to prevent violent crime. How would they? What can they learn something from what you've come up with to do some intervention, or, you know, take some measures to prevent violent crime?
We return our output to the Chicago police, so we are collaborating with them to see how is our method work, but now we don't have any result.
Thanks.
Okay, so one more question.
Thank you. I was just wondering, because American police have multiple jurisdictions over geographical areas, where in Australia we don't. We only have a single police force or two police forces per zone. And also a lot of the stuff that drives violent crime is also opportunity to be able to practice that in the first place, so the risk. And the other thing is multiple classifications of violent crime. So what some jurisdictions call violent crime, others don't. And plus you also have, as we've seen recently in the media, officers overreacting or innocent people being classed with violent crime when they actually didn't do it. So I was wondering, how much of your model have you actually checked and seen where there are false positives in there by either a misclassification or false opportunity?
Not yet, but we are... would you please say again what you mean exactly?
I think what I mean is where either violent crime has different definitions that mean violent crime,
yes,
or that people have been accused of violent crime in false circumstances. So they may be convicted of violent crime and then 2 or 3 months or a year later, it's actually proven that it was false. So in that sense, over time, you would have false people in your database that either didn't commit the violent crime or by definition, that crime actually changed. So I guess what defines someone who's been violent crime is that, for instance, they've been through the courts or they've just been arrested or they've actually been prosecuted, or have they gone through jail time? What was your defining feature?
This is what we had in the data. It was their FBI index crime, and the violent crimes was defined by the Chicago police. So we tag our individuals, violent and non-violent, based on those data. But
Thank
the
you.
result of the court.
So I think there's probably more discussion, so we'll take that offline. So let's thank Elham again.